What happens if the computer's integrity is confirmed? Let's suppose that someone stole our laptop. One of the tasks of BitLocker is to protect laptops from theft. This does not mean that someone cannot steal our laptop. It means that if someone has stole it, he can't read the data on the disk. Someone who steals our computer will probably turn it on. BitLocker will be invisible to them. The key will be read and decrypted with the TPM module. Then it will be decrypted with the next key, and finally the entire disk will be decrypted. The thief will see the login window. If our password is easy to guess and the attacker enters it, he has access to decrypted data. All investment and time devoted to encryption is useless. What then does BitLocker protect from? It protects if someone has physical access to the computer. He will not be able to run it under the control of another system other than the original. The details of the TPM modules will not agree. The attacker will not start the computer from the off-crack CD like we did previously. For the same reason, the attacker will not copy the SAM, security, and system files because he won't even know where they are on the drive. He also can't delete and he can't change their content. BitLocker, although it's not very invasive and invisible, is very effective as long as we use difficult passwords to guess. Since we have an encrypted disk, why encrypt individual files? Why do we still need EFS? Once we have an encrypted disk, we're protected against local attacks. Therefore, BitLocker is often enabled on servers as well as laptops in order to additionally ensure the safety of these critical devices. What will happen if we would like to exchange confidential data with other users? BitLocker and TrueCrypt will not allow it in any way. We need to have a solution operating in a higher layer. Not between a physical and logical disk, but between a folder and what the operating system sees, the folder content. Here, EFS comes to our aid. EFS is available since Windows 2000. The mechanism of action is as follows. To encrypt something, we need a key. If we don't have it, then when we try to encrypt the first file, our computer reports on our behalf a request to issue the certificate with a key. The request will be reported to the Domain Key Distribution Center. If such does not exist, then our computer will issue us a certificate. A public key will be in the received certificate. A private key is also linked with the certificate, which we write in the user profile. This is very important. Deleting a user profile, its loss, damage, or resetting the password involves loss of the EFS key. Now having private and public keys, we can generate a file encryption key, or FEC. With this symmetric key, we can encrypt our file. To decrypt such a file, we need to have access to the FEC key which we just talked about. Think about it as a session key. We encrypt the session key with the previously received EFS key. With the same FEC key, we can also encrypt the additional ESF keys. This is what is frequently done. These are the keys of persons with whom we'd like to exchange an encrypted file or key recovery agent. This person will be able to decrypt the FEC key and thus decrypt the encrypted files if something happens to our profile. A modular structure of the operating systems was used with the ESF. An additional component was introduced between the layers. In this case, it's the NTFS driver layer, in other words, the new technology file system. The encryption itself runs completely automatically. In a moment, we'll see. How does it look from the user's perspective? In order to ensure security, an additional NTFS driver component first checks whether we have all the necessary keys. For example, is the user profile loaded? Next, it generates a FET key, encrypting it for security. Then a backup copy or a temporary file is created. The new file is located in the same folder as the file that we wanted to encrypt. The content of the newly created file is encrypted. The file is marked as encrypted. When transferring to it data from the original file, the data itself is also encrypted. This is what happens when selecting the File Encrypt attribute. The original file will be cleared. If everything went well so far, the content of the temporary file is transferred back to the original file. The content is encrypted and remains so. In the meantime, the original file was marked as encrypted. Saving the information about the encrypted file ends the entire operation. The temporary log file is automatically deleted. The procedure is repeated if we have recovery agents or persons whose FET keys we write in the file. The final effect is that we have an encrypted file, and in the DDF and DRF fields of this file, encrypted FET keys are placed. There are as many keys as there are people who have shared access to the file. We are the one that's encrypted the file, the recovery agent, and the person we want to share the file with. The decryption procedure is very similar. First, we must have access to the FET key. To do this, we check what's in the DDF and DRF fields of the file. We read the contents of these fields, meaning the encrypted FET keys. Then we decrypt them. Having the decrypted FET key, we can try to decrypt the file itself and transfer its contents to an application. For example, display the text file in a notepad.